Hello everyone. Today we're going to get our first look at trigonometry. Trigonometry is basically all about right triangles and the relationships between the angles and the sides. So let's first start with the three triangles we have here: ABC, DEF, XYZ. And let's try to figure some things out about these three triangles we have here. Now let's say that BC is just about 3.5. Well, what could we find out about the side EF on the second triangle? Well, if we notice, ABC has to be similar to DEF, because they both have this acute angle of 23 degrees and they both have a right angle. So therefore, by angle-angle similarity, the two triangles are similar. And because they're similar, then we can set up a proportion. And that proportion would look something like this. EF, well, what side corresponds to EF? That would be BC. And we set up our other proportion. Well, what other numbers do we have to work with? Well, we have on the triangle DEF, we have the hypotenuse, DE, and which is 12. Or I'm just going to put DE for now. So what side on the smaller triangle would correspond with that? Well, AB. AB. So again, if we replace those values, we're going to have the following. EF is, well, we're just going to call it X for now, over BC, which is 3.5. Set that equal to DE, which is 12, over AB, which is 9. Well, then we're just going to cross multiply. Get X is equal to 12 times 3.5 over 9. And that's approximately equal to, and we use the say approximately with this squiggly little equal sign, it's approximately equal to 4.7. Okay, so we know that EF is approximately equal to 4.7. Now, given all the information we have, let's say about ABC, let's try to find the ratio of, in this triangle, this last one over here, YZ over XY. Well, again, this triangle XYZ has to be similar to ABC because they both have a 23-degree angle, that acute angle, and a 90-degree angle. So they're similar by angle-angle similarity. So how can we actually find out what that's equal to? Well, what side, if we look at here, YZ over XY, that's the side opposite to our acute angle, which is this one, opposite to that angle, and the hypotenuse. So let's look at AB. Well, what side is opposite to the acute angle? That's going to be BC, or 3.5. So we're going to get 3.5 over the hypotenuse, which is 9. And if you calculate that out, you should get a value that is, well, we're just going to use the just about equal to 0.39. Now, why are we figuring this out? Why does this whole proportion right here matter? Well, in fact, the proportion of the length of the opposite of an acute angle of a right triangle over the length of the hypotenuse is a very, very, very common ratio that we use. In fact, so common, we came up with a specific definition for it. So looking, again, I'm going to redraw the triangle ABC, maybe a little bit bigger this time. This is 23 degrees. This is our right angle here. We have A, B, and C, where BC is that side opposite to the hypotenuse, or I'm sorry, opposite to the acute angle, and let's just call that A. And our hypotenuse is, of course, C. And we're going to call the remaining side B. Our first definition in trigonometry is called sine. We say the sine of A, and by capital A, I mean the angle A. What angle A is that acute angle here. The sine of A is equal to, and first we're going to use our really long definition, length of the side opposite to the acute angle. We even stretch it out a little bit further. Of a right triangle. And this is all assuming right triangles. So in the bottom part of the ratio, it's the length of the hypotenuse. Length of the hypotenuse. And that is our proportion. And this is so important. Again, we created this specific definition, the sine of A, to describe that proportion. Now this is usually abbreviated in the following way. Sine of A is equal to, we just say opposite over hypotenuse. Or if we're looking at the sides of the triangle that we have, or it's just A over C. Makes sense, right? And in fact, this, well, the work we were doing earlier is very important, because if we scroll up here, all these triangles that are similar, right? They all have that 23-degree angle. And we found out that the ratio of the opposite angle to the acute angle, or the opposite side of the acute angle, and the hypotenuse was equal to 0.39. So we've essentially found out that in any right triangle that has an angle of 23 degrees, that the sine of that angle is always going to be equal to 0.39. So again, what we did, all the work we did over here tells us that the sine of 23 degrees, again, that's our angle A, our angle D, and our angle X, is always just about equal to 0.39. And it all comes from that proportion that we found out just through similarity of different right triangles. So that is the first definition of our trigonometric formulas.